Well, good morning, everyone. Today we've got an exciting lesson. It's the final lesson on our series on waves, and today we're going to be talking about the idea of superposition of waves and interference. So, let's get started. So, superposition, what is it? Well, let's start out by taking a look at this picture. You'll see we've got some ducks here swimming in a pond. This isn't my original picture, but it's found on Wikipedia. I'll put the link to it down in the description here. But you can see these ducks are floating in this pond, and as they're swimming, there's a couple things happening. First of all, they're creating their own smaller waves as they go by, and you can see these sort of trail of waves behind each one of the ducks as they go. But there are some bigger, larger waves that are kind of diagonal across the screen. You can see them, here by this mother duck. You can see that these waves interact. And if I zoom in a little bit here, you can see in this area, particularly right in front of the duck, you can see that the waves are beginning to interact. You have both the large waves that are coming across the lake and the smaller waves that the duck is creating. So that's all it is. That's all the principle of superposition is. The idea that when waves interact, they can either build up, or maybe if you have a smaller wave or a wave that's going the opposite way, the waves can make themselves smaller. They sort of overlap with each other. And when these waves overlap, they change the fundamental shape of the wave. So let's dive into this in a little bit more detail. Superposition and interference. Okay, so the idea of superposition is pretty simple. Like I said, it's the idea that waves interact. So for instance, if you have a wave that is doing this, and then you have another wave that ends up interacting it, doing something like, I don't know, maybe this sort of thing. You'll notice that these two waves are always going the same way. When the black wave is up, so is the red one. When the black wave is down, so is the red one. So when they interact with each other, when they overlap on top of each other, we're going to get a resultant wave that ends up being quite a bit bigger. It might look something like, let me use a different color here. It might look something like this, where it's gotten quite a bit bigger because you have both of those waves interacting. Something like that, maybe, is what we might see. Now, these waves don't have to be the same frequency or wavelength either. You might have one big wave sort of like this, and you might have a smaller wave doing something like this. And if you get this sort of thing going on, if these two waves were to interact, you might end up with a resultant of one big wave that kind of has these little wiggles on it from the smaller wave. And it might end up doing something like this. So all the idea is for superposition is that these waves can overlap, and when they overlap, their positions sort of affect each other. They interact, and if they're going the same way, they make each other bigger. If they're going opposite ways, on the other hand, they might make each other smaller. So let's say you have a wave that starts off like this. Here's a fairly decent large size wave. And let's say it overlaps with another wave that happens to be going the opposite way. This one's going to be a little bit smaller though. So this one happens to be going always opposite what the black one is doing. So when the black one goes up, the red one goes down. And when these two waves interact, we're probably going to get something that's going to be smaller than that original wave because some of it got canceled out by the red wave. So we might see something like this as our resultant wave, where it's made it kind of smaller, and I didn't do a great job drawing that because that should have been about the same length from here to here as it is from here to there. But just pretend I drew that right. Okay, now sometimes you might have what we call yeah. Now, sometimes you might have two waves that are going in exactly opposite directions and end up being almost exactly the same height, or perhaps exactly the same height. So if you have a wave doing this, where you notice my amplitude of this wave is kind of one space on this piece of paper here, and if you have another wave that is doing this, where its amplitude is also one space on that piece of paper here, and you'll notice it's also going at the same frequency, the same wavelength. And if you have that, these two waves may end up completely canceling each other out. You might end up with something like this, where it's just completely flat when those two waves interact. But then after they pass through each other and move differently, and once they separate, you might see those waves again. So this idea of the waves interacting in ways that can make it smaller, or even back up here in where these two waves interacted to make it bigger, that is what is called interference. It means two waves are interacting in such a way that they may make it bigger, or they may make the resulting wave smaller. Now there's two types of interference, one for making it bigger and one for making it smaller. When it gets bigger, we call that constructive interference. And when a wave gets smaller, we call that destructive. Oh, if I could spell destructive. There we go. Destructive interference. Okay, so we have constructive and destructive interference. This is obviously when it gets bigger, and destructive obviously means when it gets smaller. And if it's perfectly destructive, you end up with this flat line right here where it's completely gone. Okay, so what are the conditions we need to know in order to understand interference? Well, you might have two waves. Let's pretend that we have a couple waves like this, and I'll tell you what, I'm going to draw this a little bit more carefully. So I'm going to draw this wave like so. And then to make sure I maintain the same sort of wavelength here, I'm just going to copy that and I'm going to paste it a couple times so that we have a nice wave that looks like this. Bam. There we go. Beautiful. Now, let's pretend that this wave was infinite in size. That means we can see where I've stopped drawing it, but in reality, it keeps on going all the way out to the right and all the way out to the left. Okay, and then I'm going to have a second wave that's going to interact with that. So I'll just copy that. I'll paste it. Maybe we'll turn its color, I don't know, how about red? So we have these two waves now. And you can see that these two waves are exact copies of each other. They line up exactly when they are put here. So if we had these two waves sitting on top of each other, we would have constructive interference. These two waves would come together and make a much larger wave. Now, if I shift this wave a little bit, like, let's say that far, you can see that there's also going to be constructive interference, because every time the wave in blue goes up, the wave in red also goes up. And every time the wave in blue goes down, the wave in red also goes down. So we're going to have constructive interference here. How far have I shifted this? Well, I've shifted it. I kind of don't want to lose that red one here, so I'm just going to slide that down here for a minute. I've shifted it from here to here, which, if you remember, from any point to another point along the line is going to be called a wave. From any point to an identical point on the line is going to be called a wavelength. So I have shifted it one wavelength in order to have constructive interference again. Now, I'll also have constructive interference if I start here again, if I shift it all the way over to here. Okay, so again, I've shifted it another wavelength. And remember, we said pretend these waves are infinite, so they're going to be lining up every single time that these waves are on top of each other. So it's there, and there, and there, and there. And I could shift it the other way too. I could shift it way over here, and I could go over here, and I could keep on going. And I could do this infinitely, right? But the key here is, in order to have constructive interference, I have to shift it by a multiple of a wavelength. So that means the shift, a lot of times we call that delta L. And delta L is going to be how much we shift a wave. How far is the difference in length that the waves are traveling? How far have we moved it? Well, that amount that we have moved the wave, delta L, is going to have to be equal to, and this is only for constructive interference, it's going to have to be equal to some multiple of the wavelength. So we're going to use lambda here, and in front of that lambda, we're going to write the letter m. That m stands for any integer. M could be any integer. And how do you know which one to pick? Well, if the waves are right on top of each other, they're being created in the same place, and they're doing the exact same thing, m is going to be 0, because there is no difference in how much it shifted. If we shift it this way, one wavelength, well, now m is 1. If we shift it this way, now we're at 2 wavelengths, so m is 2. It's just how many wavelengths have we shifted this wave. Likewise, if I take this thing and I decide to shift it the other way to here, now it's gone 1 wavelength to the left, so we'd probably use a -1 there. So that's how we would get constructive interference, specifically constructive interference. I should probably label that here. This is for constructive interference. So when those two waves overlap and satisfy this equation, then you have constructive interference. Now, it turns out you could also have destructive interference too. All you need to do is have the waves go opposite directions. So instead of starting here, well, we will start here again, but we still got to shift it again. And we can do that by shifting it, maybe, instead of a whole wavelength, maybe we've only shifted it that far. And when we shift it that far, you can see every time the red one goes up, the blue one's going down. Every time the blue one goes up, the red one's going down. So they're going to be trying to cancel each other here. We're going to have destructive interference here. And how much have I shifted it? Well, I haven't gone a whole wavelength. I've only gone half a wavelength, if I can get that right again. So for destructive interference, it's going to be a half wavelength shift. Or maybe I could shift it all the way over here, and now I've gone 1 wavelength to here, plus another half to there. So that's 1.5 wavelengths. Or maybe I've gone 2 wavelengths now. 2.5 is where it'll appear. This is 3. This is 3.5. So it turns out we're going to get destructive interference every time we have a half wavelength. Or going the other way. So here, now I've gone in the negative direction a half wavelength. Or maybe 1.5. Or maybe 2.5. Does everybody see that? So what does this mean? If we want to get destructive interference, it's going to look like this. The conditions for destructive interference, let's use a different color for that. How about red? Destructive interference is going to happen when delta L, remember that's how much we shifted that second wave, is going to be equal to, well, it's every half, right? So it's got to be m plus 1/2 times lambda. So every time we have, oh, and remember, again, m can be any integer. So it's going to be 1 plus 1/2, 2 plus 1/2, 3 plus 1/2, and so forth. All right, so here we are in a program called Audacity. And in this program, it's a free program that you're free to download, and you can play around with all sorts of sound and do a lot of sound tinkering and mastering even, and you can do a lot of really cool things with it. But I'm just going to do something very simple. I'm going to generate a tone, and this tone is going to be 440 hertz. It's going to be a sine wave. 440 hertz, and I'm going to use, normally it comes with an amplitude of about 0.8 or something. I'm going to do 0.2 because I don't want to overdrive anyone's speakers, and I want it to be fairly subtle. So, a 440 hertz pitch, it's a sine wave. You probably can't tell unless we zoom way in on it here. So let me try zooming way in, and yeah, there you can see that's a sine wave. But you'll notice here it's going back and forth really fast. This is 1.2 seconds. This is 1.3 seconds over here. So in that tenth of a second, it made, gosh, I don't know, 50 or 40 something repetitions, maybe 44. So because of that, you'll see I generated a 30-second tone here, and it's going to sound like this. Okay, so that probably wasn't particularly surprising or anything particularly weird. It's just a little tone, right? However, when we have this, uh, you can actually get constructive and destructive interference depending on what your setup is. Now, if you're wearing headphones, this isn't going to work very well. But if you have two speakers, or even if you have a laptop, usually laptops have two speakers built into them. Some only have one. But if you have two speakers and they generate that tone and they play it, if you move your head back and forth, and left and right and forward and backward, and just kind of move your head around, you don't have to move it far, maybe a foot in each direction. If you do that slowly, you will start to notice that there is some sound there. And that sound that you're hearing is actually due to constructive and destructive interference. In some places, you will hear it to be slightly louder. In other places, you'll hear it slightly softer. And that's all because of that constructive and destructive interference. So I'm going to play this sound again. I'm going to ask you if you have a laptop or a computer with two speakers connected to it. Just leave them where they are. Don't turn it up at all. And just move your head left and right, forward and backward, and you should be able to hear some very subtle changes in the volume that you hear. In some places it'll be a little bit louder. In other places it'll be a little bit softer. Ready? Here we go. All right, so now everybody's going to have that sound stuck in their head the rest of the day, and their ears are going to be ringing. But you probably noticed that you did hear places, if you set up your system, you probably did hear slightly louder and slightly softer. It's a subtle difference, but you can actually hear that. And that's just due to interference, constructive interference where it's louder, and destructive interference where it's softer. So how can we use this in some sort of real life situation? Well, it turns out that we can have certain problems based on this. So let's imagine, for instance, we've got a speaker here, we've got a speaker here, and we have a person over here who is standing here. And we want to know if we change the separation of these speakers. So let's call that delta L, the distance. That's the difference in distance that the sound has to travel. So if we were to say this is the sound 1, so that's L1, and then this distance is the sound 2, so that's L2, this would be the distance between them, the difference in distance between them, so that would be delta L. So the distance between our speakers, if we change the distance between those two speakers, we can actually change what this person hears. So, for instance, Let's say we're playing a frequency of 440 hertz. And many of you know that's a tuning note A. That's a middle A. And our frequency is 440 hertz. If we take that 440 hertz frequency, we play it through these two speakers at the same time, in phase. So they're being driven by the same computer or recording or whatever it happens to be. It's going into them, computer maybe. So here's the two speakers driven by your computer in phase, and we're getting a frequency of 440 hertz. I want to know how far apart should the speakers be in order to produce the quietest sound. So how far apart should we put them in order to produce a quiet sound? Not a loud sound, but a quiet sound. So the first thing you realize is when we say that quietest sound is going to mean we're looking for destructive interference. If we want destructive interference, that's going to mean that we're going to use this formula. Delta L has to be equal to m plus a half times lambda. With that being the case, we don't know lambda yet, but we do know something. We know that the speed of sound is 343 hertz. And so, hertz, yeah, 343 meters per second. There we go. Okay, so because of that, we can solve for lambda using this equation. V equals F lambda. We'll solve that for lambda, so V over F is equal to lambda. And then we plug in our two things, 343 meters per second divided by 440 hertz is going to be equal to, let's see, when I do this, I got 0.795, let's call that 780. We'll say that's approximately 780 meters. Okay, so there is our wavelength. Now that we have that, we can plug that into this equation up here. But there's one thing we need to be careful of, and that is, what is m? Well, delta L is equal to, the easiest way to solve this problem is to use m is equal to 0. If m is equal to 0, that will give us the first time their separation is going to work. If we use anything else, 1 or 2 or 3 will also work. You'll get different numbers from that, but it turns out you'll get quiet spots whenever they're separated by that much in this configuration where the person's standing over there. So 0 plus 1/2 times lambda is 0.780 meters. The 0 really doesn't matter, so it's just a half times 0.780. And delta L is equal to, when I do this, I get 0.390 meters. So how far apart do the speakers need to be? 0.390 meters, or about 39 centimeters. Let's try one more example that's a little bit closer to what we just saw. So let's imagine we have a speaker here and a speaker here, and they're separated by a certain distance. Maybe let's make them, I don't know, keep the math easy, 1 meter apart. And let's say there's a person over here, and he's walking from this speaker out this way. So he starts off here, where he's really close, and he starts walking, and eventually he hears it's getting quieter, and then it gets back louder, and the loudest spot happens to be out here. So maybe this loudest spot is going to be when he's walked out, I don't know, 0.5 meters. Let's call it that. And let's make these speakers play a frequency of, let's try something a little bit higher. Actually, I'll tell you what, let's look for what that frequency is. We don't know what the frequency is. But this guy, he knows that when he walks out 0.5 meters, he hears a loud spot there. And we want to know what is the frequency that these speakers are playing. Well, in order to do this, we know if it's a loud spot, we are using the formula for constructive interference. We know delta L is equal to m lambda. The only problem is we need to find out what our delta L is. Well, delta L is how much the waves have shifted because of the difference in distance. So, okay, that's easy. 0.5 is going to be part of it. But we also need to know the distance to the speaker over there. If I call this L1, this would be L2. And the distance to that speaker over there, we can use, that's a right triangle, so I can use the Pythagorean theorem. So L2 is going to be equal to the square root of 1 meter squared plus 0.5 meters squared. And when I get this, L2 is equal to, give me a second here, let me use my calculator. Should probably be doing this yourself too. So square root of 1 squared, and it's just 1, plus 0.5 squared is going to be, I get 1.118 meters. Okay, so now that I have that, what is the difference between the two paths? Well, it's going to be so delta L has to be equal to 1.118 meters minus 0.5 meters. That's going to be equal to 0.6, right? Let's see, minus 0.5, yeah, 0.618 meters. All right, so there is our delta L. Now our delta L has to be equal to m lambda. If m was 0, the easiest solution, well, this wouldn't work. Why? Because if m is 0, we try to divide by 0 and the whole thing blows up. And really, m would be 0 when the difference in paths between the two would be exactly the same. The difference in paths here, when they're exactly the same, how can you get that? I don't think you can in this configuration. It would be the same if he was in the center, but he's not in the center. So because of that, we can't use m equals 0 in this situation. So the easiest thing to do then is to use an m equals 1. So let's go over here. We will have m equals 1, and we would get delta L is equal to 1 times, lambda right there. Oh, and I should have substituted in my delta L here, which was 0.618 meters. All right, well, that's pretty straightforward because you can see this 1 times lambda is just lambda. So we already know that the wavelength is 0.618 meters. Okay. Now that we have that, we can find the frequency because we know this is sound again. So V equals F lambda. Solving that for F, F is equal to V over lambda. That's equal to, speed of sound is 343 meters per second, divided by lambda is 0.618 meters. And when I do this, 343 divided by 0.618, I get somewhere around, and I used the exact answer when I did this, I got 554.986, call it, hertz. So it's going to be a little bit higher pitch than what we were working with there, but it turns out that pitch will give us a loud spot if we are half a meter in front of it and the two speakers are separated by a meter. So you can actually tell what that frequency is just by the setup of the system and by where you hear loud spots and soft spots.